So hello everyone. In today's lecture, we are going to deal with the different types of dispersions. Apart from that, polarization mode dispersions, the main concept that we are supposed to deal. And before moving into details about the polarization mode dispersions, let's take a quick review about what is dispersion. Dispersion is basically a spreading of a optical signal. Whenever your optical signal is passing through an optical fibers, so with the help of a total internal reflections, it is propagating inside the fiber and coming at the end of the fiber. Now, there are various phenomena that deals to that overlapping of optical signals. Now, the phenomena that deals with the overlapping means dispersion is called as the phenomena which leads to a spreading of a pulse. Whenever there is a spreading of a pulse, we say that a dispersion is occurring. So this is the dispersions, and dispersion is of three main types. First is your intramodal dispersion, intermodal dispersion, and the polarization mode dispersions. In this intramodal and intermodal dispersion basically occurring because of the different mode propagating through the optical fiber with a different velocity. So if they are propagating with a different velocity, different modes, so whenever they are arriving at the end of the optical fiber, they will arrive at a different time. So this leads to a spreading of a optical pulse. So in the intermodal dispersions, different mode travel with a different velocity. So this intermodal dispersion is not going to occur in the single mode fiber. It's only going to occur in the multi-mode fiber, because multi-mode fiber supports multiple modes through the optical fiber, where single mode fiber is supporting only a single mode. So if there is a single mode, there is no concept of an intermodal dispersions, but there will be an intramodal dispersions. So apart from that, we are having a polarization mode dispersions, like the polarization means the orientation of an electric field. Whenever your optical wave is traveling through the fiber, so where the orientation of electric field is, that is going to tell us the polarization of that particular optical signal. So apart from all these three, let us first try to define each and every one in details. And intramodal is basically dispersion is combination of a waveguide as well as the material dispersion. This one, material dispersion and the waveguide dispersions. Now, this material dispersion is occurring because whenever the light is it's entering through the optical fiber with the help of an optical source. So the optical source must be having a different colors. So that different colors, whenever they are propagating through the optical fibers, as they are encountering a refractive index, so these different colors emitted from the optical fiber, they will travel with the different velocities. So if they are traveling with the different velocities, as each wavelength will be behaving in different way for a particular refractive index of the fiber. So if they are behaving in different way, means that they will travel with a different velocity. So if they are traveling with a different velocity in an optical fiber, definitely they are not going to arrive at the same time at the other end of the fiber. So they will arrive at a different instant of a time. So if they are arriving at a different instant of a time, this leads to a spreading of an optical pulse. So that is concept for a material dispersions. So we have already dealt through these basic concepts. Quickly moving to the polarization mode dispersions. So now this polarization mode dispersions is occurring due to the variation in the fiber core diameter. Due to the variation in the fiber core diameter in a single mode fiber, because the two orthogonal polarizations, that means electric and a magnetic field, they are going to be at the perpendicular to each other and to the direction of propagation of the wave. So if we are saying a direction of propagation of a wave in that directions, so what will be happen to the your electric and magnetic field? It will be perpendicular to each other as well as to the direction of propagation of wave. Now in this, these two orthogonal polarized modes, what they are happening, the variation in the fiber core diameter may leads to the presence of non-uniform stress or bands along the length of the fiber. So it gives rise to a, that means they are going to arrive after different times because of difference in the group velocities among the light rays, which give rise to a pulse broadening. So that is because that is the polarization mode dispersion. So now let's move to the directly to the slide of a polarization mode dispersion. So in this polarization mode dispersions is defined as the difference in the propagation time between two orthogonally polarized components of light pulse in single mode fiber. Now if these two orthogonally polarized components, they are traveling with the different velocities, if they are traveling with a different velocity, definitely they are not going to arrive at the other end of the fiber perpendicular to each other. There will be a slight difference in the 90 degree. I mean, there will be a slight difference of when they will be not perfectly orthogonally polarized, there will be some deviations. So that means they are going to arrive at a different time, instant of a time. So if they are having a different instant of a time, this leads to a broadening of the pulse. So as with the help of this diagram, so here we are having a two orthogonally polarized mode. So due to pulse broadening, what is happening? They are not arriving at the same instant of a time. So there is a delay, and due to this delay, which is known as delta tau PMD, which is delay, that is a polarization mode dispersion, I mean delay of a polarization mode dispersion effect. So that is delta tau PMD. PMD is polarization mode dispersions. So different in the polarization mode propagation time as an optical pulse passes through a fiber with varying birefringence along its length. So how we can calculate that is something given by this formula, that is delta tau PMD is equals to mod of L upon VGX minus L upon VGY, where this VGX and VGY are the group velocity of two orthogonally polarized mode. So one can easily calculate the polarization mode dispersion delay with the help of this formula. So you should be knowing about what is the length of the fiber through which this wave is propagating and the group velocity of two orthogonally polarized wave. Definitely these two group velocities not going to same, they must be different. Because of the difference in the group velocity, they are arriving at the end with a different instant of a time. As a result, it leads to a broadening of a pulse. So suppose that let's try to visualize the concept of a polarization mode delay with the help of some example. So in this example, we are considering of optical fiber of a 1 kilometer long distance. We have considered a multimode fiber, multimode step index fiber, having a refractive index N1 and N2 as well as relative refractive index difference delta is given as 0.01. Now the question is, what is the modal delay per length in the fiber? What will be the modal delay per length in the fiber? So let us try to visualize it. That is, your delta t is given by L N1 square delta upon C N2. Now the question is, from where we are getting this formula? Now in order to get this formula, first of all we have to build some concept. That concept is related to whenever we are dealing with the multimode optical fiber. So in that multimode optical fiber, we are assuming that there is a axial ray as well as there is a meridional ray. Now these two rays, whenever they are propagating through the optical fiber, meridional ray, they are going to propagate through the total internal reflections. That means they will pass through the central axis of the fiber, and with the help of a total internal reflection, they will propagate through the optical fiber. Whereas the other ray, which we call as axial ray, which is only traveling through the center axis of the fiber. That means they are not going to fall at the core and clad interface. They will directly pass through the central axis of the fiber. Now that is only possible because of the highly concentrated source, laser source. With the help of a laser source, one can easily do that. So we are going to consider two different rays. So let us try to visualize that thing with the help of this one figure. So in this figure, we are considering a optical fiber, and in that optical fiber, we are saying we have a clad. This is your clad, as well as this whole region is your clad, and this middle region is your core. In this, we are considering two rays. First ray, which is directly passing through the central axis of the fiber, and the other ray, that is meridional ray, which is hitting at the air and core interface axis. So this is the meridional ray, whereas the other ray, there is also other ray possibility, which is called as a skew ray. So skew ray will incident at the core and clad interface apart from the central axis of the fiber, whereas meridional ray will always incident at the core and clad interface through the central axis of the fiber. And when they are hitting at the core and air interface at the central axis of the fiber, they will maintain a acceptance angles. They will have an incident angle which is less than the acceptance angle. So if it is less than the acceptance angle, definitely they will refract after passing through the air and core interface, and whenever they are striking at the air and clad interface, they will strike at an angle which is greater than the total internal reflect, which is greater than the critical angle. So if it is greater than the critical angle, obviously they are going to follow the total internal reflection phenomena, and it is due to this phenomena that your ray is propagating through the central axis of the fiber. So we are considering two rays. One is the meridional ray and the another one is the axial ray. So this is your axial ray. Now what we have to do, we have to calculate what is the delay that is occurring between these two, axial and the meridional ray, at the extreme end of the fiber. We will consider some length of the fiber and we are passing two rays. First is axial ray, another is meridional ray, and at what instant they are emerging at the extreme end of the fiber, we are going to calculate that delay. Through that delay, one can easily establish the time delay in the between the rays in the case of your multi-mode optical fiber. So what we are considering first is the time taken. We are considering the time taken for the axial ray to travel along a length of a fiber, which we have considered the length of a fiber as L. Now it gives the minimum delay time T min, because it is traveling through the central axis of the fiber. So definitely they will arrive at a time much before than the meridional ray, because they are traveling through the central axis, whereas the meridional ray is first hitting the core and clad interface. After total internal reflection, it is again hitting the hitting the core and clad interface at the next reflection. So in this zigzag path, they are moving through the optical axis, optical fiber, whereas your axial ray is passing through the central axis of the fiber. So definitely they will arrive, they will take much lesser time in comparison to the meridional ray. Now what is the time taken by the axial axis, axial ray? It will be the distance covered as by the velocity. So the distance covered that we have taken is your L, that means length of the fiber. And what is the velocity? We know that the phase velocity is given by an expression, or the velocity is, with which a wave travel inside the some medium is given by c by n1. So that is the velocity, and what is the expression that we got is ln1 upon c. So we are considering this equation as first equations. Now where n1 is the refractive index of the core and c is the velocity of light in vacuum. Now the next thing we have to calculate, we have calculated the minimum time taken by the axial ray. Now we have to calculate what will be the maximum time taken by the meridional ray. Now this maximum time taken by the meridional ray is something given by what is the distance traveled through the meridional ray, as well as the what is the velocity with which it is traveling through the optical fiber. So it is given by L by cos theta upon c by n1. So it will become c n1 upon c cos theta. So this is the maximum time taken by the meridional ray. Now as per this figure, what is sine phi c. Sine phi c, we know that with the help of Snell's law, your critical angle is given by sine inverse of n2 upon n1. That means sine phi c is equal to n2 upon n1. So if I want to calculate it in terms of theta, that means the value with which the angle with which a ray is refracting at the air and core interface, that theta can be given by sine 90 minus phi c. This is your 90 degree, and theta will be 90 minus phi c. So in this way we are getting this cos theta. Phi c is what? Phi c is pi by 2 minus theta. So what is pi by 2 minus theta in terms of sine? It will become cos theta. So your cos theta is equal to n2 upon n1. So we will directly put this value inside this formula, and it will become L n1 by c and n2 by n1. So it will become L n1 square upon c n2. So we are giving the name of this equation as the fourth, and with this difference, that means T max minus T min, that means the maximum time taken and the minimum time taken by the two rays that we have considered, will give us the what is the propagation delay between these two rays. It helps us to establish the formula between the two rays when they are propagating with the optical fiber, through the optical fiber. Now this difference we can easily calculate from, we got the T max and this is your T min, and if you are subtracting T min from the T max, that is going to give you what is the time delay between these two waves. So after subtracting, you get this formula, ln1 square upon c n2 into n1 minus n2 upon n1. And what we know that relative refractive index is given by n1 minus n2 upon n1. So we will equate it by delta, and now it is becoming L n1 square del upon c n2, and this is your del ts, time taken by two rays whenever they are propagating through the multimode fiber. Now we are going to use this formula. We are going to use this formula in the numerical that we have considered, and we will try to establish calculate the propagation time taken by these two, or propagation time through the multimode optical fiber. Now this is the question that is asked: what is the modal delay per length in the fiber? Now the modal delay per length in the fiber, we have already discussed that it is given by L n1 square del upon c n2. So del t will become L n1 square del upon c n2. So from this you can calculate the time taken, and if you are dividing it by a length, it will become that delay that is occurring per unit length of the fiber, and which is what asked in this question also. The question is, what is the modal delay per length in this fiber? So if it is per length, you have to divide that delta t with the L, that is length. So it will become del t by L. So we are already provided with all the parameters, n1, delta and n2. So if you are provided with all the parameters, you can directly calculate the result and find the what is the pulse broadening. So we got that 50 nanosecond is the broadening of a pulse. That means two pulse are out of two ray, they are occurring at a different instant of a time, and that different total delay is 50 nanosecond. So total delay is 50 nanosecond occurring in each kilometer of a fiber, right? So this is what is your pulse broadening through the multimode fiber, and we will get this answer. Now one can easily calculate the what is the polarization mode dispersion delay if you are provided with the group velocities of the two modes. That one is L upon Vgx minus L upon Vgy. So till now what we have studied? Till now we have studied the two concepts, that means attenuation as well as dispersions. These two concepts is something which is degrading the quality of the optical signals. Attenuation is what? Attenuation means decrease in the strength of the optical signal or optical wavelength whenever they are propagating through the optical fiber, and that decrease in strength of the fiber is something following a exponential decay. So that exponential decay is giving us the attenuation through the optical fiber. In that also we saw that attenuation is basically occurring because of two phenomena. One is called as scattering or spreading of whenever ray is passing through the optical fiber, and because of the different particles present during the manufacturing process, they are going to reflect the light in different directions. As a result of that, scattering will occur. So now this is called as the scattering. Another one is called as the something we call as a intrinsic and extrinsic factor that leads to the phenomena of attenuation. That intrinsic factor is basically because of the material. Your fiber is made up of silica. So if it is made up of silicon dioxide, definitely your silica is bonded with the two oxygen atoms, and this molecule will be having its resonance frequency. And if your optical signal or optical wavelength or frequency, better word is frequency, is striking at the molecules, if this frequency matches with the resonance frequency of that molecule, silicon dioxide, so if they are matching with that frequency, that leads to the absorption of a optical signal. So if optical signals are absorbed, there is no way to get back that signal. It's totally lost. Whereas the other way of getting is called as a radiation, radiative modes. So in that radiations, which is also occurring because of phenomena like scattering and bending. So in that scattering, once in that radiation, once any optical signal is deviated from the main path of the optical signals, so it's not like that it's totally lost. You can get that power. But in the case of absorptions, once your optical power or a photon is absorbed, you cannot recover back that photon. It gets lost in the form of a phonons, that means vibrations of the molecules. So that's why these two phenomena, because of these two parameters or these two behavior, your attenuation is occurring. Apart from that, we know that dispersion. In the case of a dispersions, we are having a the concept of a pulse broadening. So as your optical signal is propagating through the fiber, because of the various parameters like your source, whenever you are incidenting a light from the light source, so there could be a different frequencies that is traveling through the optical fiber with the different velocities. And if they are traveling with different velocity, definitely they are going to arrive at the extreme end of the fiber with at a different time instead of a time. And this arrival at different, or this mismatch between the timing, leads to a spreading of an optical pulse. So that is called as a dispersions. Apart from that, this dispersion is of many types, like three types. We have broadly categorized into three types: intra, inter, and polarization mode dispersions. Your intermodal dispersion is basically occurring in a multimode fiber, whereas your intramodal is basically concentrated in the single mode fiber. And in the case of polarization mode dispersions, like if two orthogonally polarized mode, they are not traveling with the same velocity due to some variation in the refractive index. So if not traveling, so definitely when they arrive at the extreme end of the fiber after traveling through a certain length, we call it as L. So these two orthogonally polarized will be having a different group velocities. So there will be a time mismatch between their arrival. So that leads to a polarization mode dispersion. So that polarization mode dispersion is something given by this formula, that is delta tau PMD. Also, we have established a relationship which is called as a modal delay whenever we are considering the multi-mode optical fiber. In that, what we have considered? We have considered the cylindrical geometry of an optical fiber, and in that cylindrical geometry of an optical fiber, we consider two rays. First, we call as an axial ray, another we call it as a meridional ray. Now, this axial ray will always propagate through the central axis of the fiber. On the other hand, this meridional ray will propagate through the optical fiber in a zigzag path, as they are following the total internal reflection phenomena. So, they are striking at the core and clad interfacing, and with the help of multiple total internal reflection, they will travel through the optical fiber. And if we are calculating a delay between these two rays, then it could be easily help us to establish what is the modal delay that is occurring inside the multimode fiber, because we have considered these two rays. So, what is the formula that we have calculated? Is called as this formula, that is delta Ts is equal to Ln1 square del upon Cn2. So, this formula help us to establish the relation. So, with this, we have taken the numerical. Also, we have tried to evaluate that formula. We have tried to apply that formula concept of a modal delay with the help of example. We calculated what is the modal delay per unit length in the fiber, and this is what we have taken with the help of example. What is the modal delay that will occur through the multimode fiber? So, in our next class, we will try to build the concept of a Kerr effect, which is due to the non-linearities in the optical fiber, and we will try to solve some more numericals that is covering the unit 2, and also some important numericals that will be covering unit 1 before start of your unit 3. So, we will try to cover all this concept in our next class. Thank you all.